In this video, we continue with hypothesis testing in the VAR model. So we would like to be able to test hypotheses of this very general form, which includes hypothesis testing of individual parameters or joint hypothesis testing of several parameters. Now, since we rely on maximum likelihood estimation, the likelihood framework allows us to make use of three types of tests: the wall test, the LM test, or the likelihood ratio test. Now, all tests are asymptotically equivalent, so none is preferred from a theoretical point of view. But in practice, some might be easier to compute than others, so there might be practical reasons for preferring one test over the other. Let's have a closer look at each of them separately to see which test might be preferred in which situation. Let us start with the walled test. Now, under our null hypothesis and the assumptions of our proposition, where we established asymptotic normality of our unrestricted parameter estimator, we can derive the asymptotic normality of this guy over here. Now, what is this guy? It is nothing more than a linear transformation of our unrestricted parameter estimator. So the estimator, as you would have seen in the previous video, which I denote with pi hat u for unrestricted model. And we can rely on the delta method to determine its asymptotic variance. So this guy also goes in distribution to a normal. And how can we obtain the asymptotic variance? Well, we start from the asymptotic variance we had before, plus pre and post multiplication with the gradient of this guy with respect to pi, which is then nothing more than the matrix C that contains the information on which hypothesis that we exactly want to test. The walled statistic is then given by this form over here, where you can show that it follows a chi-square distribution under the null. Now, how should we understand this walled test intuitively? Well, the walled test checks if the regular unrestricted estimator, so where no restrictions are imposed, you just estimate the model by least squares, is close to satisfying the linear restrictions as set out under the null hypothesis. Now, if it strongly disobeys the restrictions from the null, then this term over here would be large, giving us a large value of the test statistic. And so we would reject the null for large values of the test statistic. Now, when would we like to make use of this test in practice? Well, when it is easy to obtain the unrestricted parameter estimates. Now, let us move on to the second test, the LM test, or also sometimes called the score test. This test is based on the score, namely the derivative of the log likelihood with respect to the parameter value. And we evaluate this for the so-called restricted parameter estimate, denoted by pi hat r, which are the parameter estimates we obtain from the model where the restrictions as set out under the null are imposed. Again, the corresponding test statistic follows a chi-square distribution. Now, intuitively, the score at the true parameter should vanish. It should be equal to 0. We, of course, can't check the score at the true parameter value since it is unknown in practice. But what we can do is we can check it at the restricted parameter estimate. And if this is close to the truth, which would be the case if the null hypothesis is plausible, then we would also be getting a small value. So again, for small values of the test statistic, you would not reject the null. We would reject the null for large deviations from the score from 0, so for large values of the test statistic. Now, when would we like to use this statistic in practice? Well, when it is easy to obtain the restricted parameter estimates. But of course, realize that you need to impose the restrictions as satisfied as set out under the null to get this estimate. If the restrictions would imply cross restrictions, meaning that they would involve parameters from different equations of the VAR, that would mean that you can't simply estimate the parameters equation by equation anymore. But then you would need to estimate the system jointly, which would typically be more cumbersome. Lastly, we have the likelihood ratio test, which looks at the difference in the log likelihood between the restricted and the unrestricted parameter estimates. So both pop up under this definition. Again, the statistic is asymptotically chi-square distributed, and intuitively, when the log likelihood would not change much when we impose the restrictions or not. So for small values of the test statistic, we can do almost equally well with the restrictions imposed. So then the restrictions would seem plausible and we would not reject the null for small values of the test statistic. When would you like to make use of this test in practice? Well, when it would be very easy to evaluate the log likelihood for different parameter estimates, because then the test is just obtained by subtracting these two values. Now, after having discussed hypothesis testing in the maximum likelihood framework, another important practical issue that is still remaining is the procedures that can be used to select the order P of the VAR model. So how many lagged components of each series should be included? Now, popular methods to that end are the three following procedures: sequential hypothesis tests, information criteria, and autocorrelation tests on the residuals. The first two I will discuss in more detail. The last one involves mainly visual inspection and autocorrelation tests on the residuals, which should be multivariate white noise. I won't discuss this procedure in detail here, but if you are interested to know more, you can have a look at this book from Lutkopo. How does the sequential hypothesis test work? Now, you can start in this procedure from a very large possible lag order. Remember, we want to determine how many lags we want to include in the VAR. So let's just start from a large possible lag order. Let's say, for instance, 10 lags to make things a bit more concrete. And then we will perform a sequence of hypothesis tests, each time testing the nullity of the highest order coefficient matrix. So you can estimate the VAR with 10 lags and then test the null that the parameters at lag 10, so the highest order lag, are jointly equal to 0. Now, if you do not reject the null that all parameters are equal to 0, that gives an indication that you don't really need to go 10 lags back in time. Then you can just safely drop this 10th lag and re-estimate the model with only 9 lags, so 1 less. Again, estimate the model and test the null hypothesis then that the 9th lag coefficient matrix is jointly equal to 0. When would the procedure stop? Well, you would stop when you do reject the null hypothesis, and you can take that then as an estimate of your VAR order. Now we have seen the sequential testing procedure to determine the order in the VAR. How would information criteria work? Well, generally, first, an information criterion typically makes a trade-off between goodness of fit, or let's say lack of fit, which is a function of the likelihood, and a penalty for model complexity, which is a function of the model dimension. The goodness of fit typically increases when we include more parameters in the model, or equivalently, the lack of fit decreases. But of course, more parameters make the model more complex. So the penalty term increases for more complex models. An information criterion then makes a trade-off between both terms and picks the model out of a set of candidate models with the lowest value of the information criterion, which then best balances these both terms. For the VAR model, the information criterion for lag order selection takes on this simple form. And typical choices of the penalty for model complexity CT here include 2 for the Akaike information criterion, or just AIC, and the log of the sample size here for the Bayesian information criterion, the BIC. BIC typically penalizes much more for model complexity than AIC does, since the term log T is typically larger than 2 for any practical sample size. The HQ criterion, which is far less popular than the other two, behaves in between AIC and BIC. Now, what is important to realize is that these constants over here, they are not set arbitrarily or chosen arbitrarily, but they pop out of a theoretical framework in which they are formalized. AIC looks at how close the approximation is to the true density of the data, and the maximum likelihood estimation tends to minimize then the distance from the true model to this approximate model. BIC, on the other hand, picks the candidate model with the highest probability given the data and is formalized in a Bayesian framework. Now, which criterion to work with in practice? Well, 2 nice properties for an information criterion would be efficiency and consistency. If we would be comfortable making the assumption that the true model is one of the candidate models, then a nice property would be selection consistency. Namely, that our selection method is able to select a true model from the candidate set with a probability tending to 1. BIC and HQ have this property. But if we do not want to make this strong assumption, but instead would like to look for a model that has the smallest expected prediction error, then efficiency is important. Efficiency is then measured through the ratio of the expected loss of the selected model to a theoretical minimum. And if this ratio converges in probability, so if this converges to 1 in probability, then our selected model would be efficient. AIC is efficient, but an information criterion can't satisfy both properties at the same time. So what to do in practice? Well, in practice, if we can't have efficiency and consistency at the same time, it depends, of course, on what you would like to do with your model and which assumptions you are comfortable making. In the context of time series modeling, people do often like to work with the BIC simply since it penalizes much more for complexity than AIC. And when you're interested in forecasting, for instance, parsimonious models often do better out of sample.